I've great pleasure today to introduce Hamid Kamangir. I've worked with him for, I bagged him, not worked with him. I bagged him for almost 2 years. And he's been trying to teach me machine learning, which is not getting into my head. But this is a great chance for other people to be able to learn what he does. Hamid is he's completing his PhD at USC Davis. People might be surprised why a PhD student to present, but he comes with more than 11 papers on machine learning. That's all I'm counting, and could be more. And he got his Bachelor of Science from Geomatic and Surveying Engineering in Shahid Raja'i University.
Yes.
This is in Tehran. And then in 2015, he got his master's in remote sensing and GIS engineering from the University of Isfahan
Yes.
in Iran. And in 2019, he got his master's, second master's in computer science at Texas A&M at Corpus Christi. And the end of this spring in May, he expects to get his PhD from UC Davis. So, and he's done quite a lot. If see the artificial neural network, recurrent, the convolutional, you name them all, transformers. So I'm really excited. I want to hear more about all these techniques which Hamid uses. And his talk today is about attention. Do we really need attention when we are doing AI modeling? Welcome to Stonebrook, Hamid. The floor is yours.
Thank you so much, Dr. Luis. That was so kind. Thank you so much. I really appreciate it. I'm so excited today that I'm here, and this is a big chance for me to know about you and presenting for you. And thank you so much again. Yes. So this presentation, I picked up this title as attention is kind of the things that we need for AI modeling, which is these days actually got a lot of attentions models. But you introduced me. I really appreciate that. Yes, I have this background, and I'm really interested in applied machine learning and deep learning models, and mainly for environmental and atmospheric, or let's say meteorological application and forecasting. And recently I got interested into the imbalance regression, mainly the deep learning imbalance regression for forecasting, which is a really hot topic as well, which I'm working on that. So in my talk today, I will go through all these details. So generally, as a data scientist, or let's say an AI modeler, I will think about the environmental and atmospheric data structure and how we can approach those data set in different way. And what has been done so far, and in the second part, and in the third part, I will talk about the FogNet, which is an architecture that we designed specifically for coastal fog forecasting for Texas South Bend. And I'll talk about the CNN's limitations and a new generation of deep learning models, which they call it attention-based model. And we need to think about these attentions, that how we can take advantage of this new generation of deep learning models, specifically for environmental models. And at the end, I will talk about the SparkNet, which is a tool that I'm developing based on the attention, specifically for different data structure of meteorological, atmospheric, or environmental modeling. So in the first part, as we know, in general, we are dealing with a 4-dimensional data structure for meteorological, atmospheric, or environmental modeling. We have a map with the 2D spatial domain of the map. We have a different variable, or let's say a variable in different altitude. And also we have time, which is the 4th dimension. So as I said, we are dealing with a 4-dimensional data structure, which each map has a 2-dimension for X and Y, and the third dimension can be a variable in different altitude or different altitude, different variables, in fact. And also we have time. And as we know, all these 4 dimensions providing a rich source of information for modeling, and we need to learn about them in a really appropriate way, in fact. But let's see what has been done so far. In one way, people try to extract the information for some specific, or let's say strategic locations, and from the maps, put them in the like a tabular data set, like a CSV file, and then fitting them in conventional statistical or recently machine learning models like logistic regression, Bayesians, random forest tree-based models, and all those conventional machine learning models, which is good because they are really simple, straightforward, and interpretable. We can easily understand what's going on within a model, and why that result is good or bad or whatever it is. But we know that they are not enough in terms of learning the linearity or non-linearity of the data structure that we are using, and interaction between the input and output, in fact. And also, since we are kind of like messing up with the data structure and maps and putting them in the tabular data, so we're losing the spatial correlation between the pixels, in fact, from the map, which for most of the cases, we need those information. We need those patterns, in fact. On top of those models, recently, because of the kind of GPUs that pop up, that 2017, etc., we were able to use the CNN models. The CNN models, since they're like having the raw input image, in fact, and by using some nonlinear kernels, they're learning the pattern from the map, which is a really good thing compared to the conventional models that we talked about them, because in these models, we are learning the spatial correlation between the pixels and those patterns, which they can be really important for environmental and, atmospheric modeling and etc. But these models are still kind of like hard to interpret the result at the same time. We need to do some post-processing to go back to see what's happening through those networks and how the model learn all those information, in fact. And also, since they are limited to the 2-dimension, they are ignoring the temporal and variable-wise interactions that kind of, in some sense, in some application, for example, they are really important to us. So the next generation came, which they're 3D CNNs. The 3D CNNs solve some of the previous problems by using the 3D kernels. They goes toward the depths, in fact, by learning the correlation between the variables, or let's say in the time, like temporal correlation in the 3rd dimension. The good things about these models, as I said, is they solve some of the problems. We are able to learn the spatial correlation plus the 3rd dimension, which can be time or different variables. But still, these models have some limitation. For example, they're still hard to interpret. They are limited to the size of the kernel that we are using in depth. For example, if you're using the 9, for example, at the same time, we are able to learn the intercorrelation between only 9 variables. If we have more than 9, we have to, do it in sequence, which that means we are not able to learn the correlation between all the input variables, or let's say the time, at the same times. So I will back to this point. And also, still, we are not able to have like a clear, distinguishable way to learn the 3rd and 4th dimension in the 3D CNNs. But still, they are like a huge, a jump for environmental modeling. So based on what I said, like 1D, 2D, 3D, we started a project 2-3 years ago for coastal fog forecasting. This is a coastal band of the South Texas, and we use a NAM output variable, which you are familiar more than me with this data set, and we use the SSD sea surface temperature more data set from the NASA repository. Per each day, we picked up a 4-time prediction, initial, 0, 12, and 24, for example, for 24 hours lead time prediction. And for each time, we had 93 different variables. In fact, that was like 15 variables, but we had each variables in different altitudes. So 93 different variables for each time and 4 times. That means 384 different variables for each day. So that's a 4-dimensional data set, right? And we need to take care of all these dimensions and all this intercorrelation between the variables in different like dimension. And as a target, we use a Mustang Airport visibility, which is we binarize it as a fog or not fog by using some threshold for less than a 1 mile, in fact. And the goal was going for 6, 12, and 24 hours lead time prediction. So based on the concept that I kind of like explained before, we picked up the 3D CNN because that was like the strongest and the best way to go for the data set with more than 2 dimensions. And we tried to learn about this different, interpolation that we have. We designed this architecture kind of like complicated, messy, but I love it. And it worked really well at that point. We tried to do some, fancy modules within our architecture based on the CNN models, and learning the spatial variable wise in different ways and separating them. And also we did some kind of new things based on this specific project, which is we grouped the input variables based on their physical similarity in different groups to help the model kind of learning those complexity in a better way and in easier way. But still you can see in this project, I was limited to learn about the 3rd and 4th dimension since I had a 4-dimensional data set. And I combined the temporal and variable-wise kind of interpolation in the 3rd dimension, which is a depth, right? Because in the 3D CNNs, we will learn in the cube. We will see the input data set as a cube, in fact, which is a 2 dimension of X, Y, and Z is all the layers of the variable that we have. I was limited to the kernel size of 9, which that means in only at the same times I have a correlation between only 9 variables, and it goes layer by layer, 9 by 9 till the end of 384 variables, which worked well, helped me a lot to kind of learning about the 3rd and 4th dimension, much better than other models that we have. But it's still limited, right? Because at the same time, I was not able to learn those intercorrelation for all the variables that I have at the same time. So the order of the variable in depth of the cube was really important at that sense. And we were so lucky that we had Valen Collins from NOAA, and he told us how to, order the variables, which that was really important. And I will show you some of the results. So in terms of the performance, this model worked really well. As you can see here, we compared the FogNet, which href, with each one of the operational physical based model for 3 different categories of the visibility, as you can see here, for 24 hours lead time prediction. You can see the result. HSS, for example, here is 50% compared to 23%, or RSS or CSS or PSS, you can see all of them. So that means this model actually, learning much better those nonlinearity and complexity of the data set for fog forecasting compared to the operational model, at least for now. From here, I'm not in the presentation mode. All right. So from here, you can see we compared the FogNet 3D because we wanted to know that how much, because the 3D CNNs is really kind of, in terms of the computational cost, it's really expensive model. So we compared that with the 2D or different other architecture that we had in the bench as a benchmark. And you can see, for example, the FogNet 3D, even compared to the FogNet 2D, which the kernel is 2D instead of the 3D, work really, outperform all those different architecture that we had as a benchmark here. And the main reason is having a 3D kernel instead of the 2D kernel. because the 3D kernel helped us to go through the depths and learning the correlation for higher dimension, not only within each map. And also we did some kind of like application study here. And as I mentioned, since in the 3D kernel, we are limited to the size of the kernel and the order of the variable are really important, we try to shuffle the order of the variables to check that one. And as you can see here, clearly it messed up the result actually. And you can see the PSS goes down even less than 20% compared to the 60 for the Fogman. That's okay. I mean, we are happy to use those 2D kernels to learn about the third and fourth dimension, but it's still we have some, you know, sensitivity of the order of the variables. We are limited to the size of the kernel and etc. We improve the result, but we have some, you know, difficulty here, and we need to take care of all those details, in fact, which is challenging. So, and also we did some post-processing to learn about the model, that what this model has learned, in fact. By using some explainable AI, we did some permutation, by using some feature group holdout, loss shap, and you can see the paper in, which I have referenced here. We would try to learn that what the model has learned, in fact, about the patterns, about the correlations, and etc. Which that was also helpful. I know that was like, again, like a huge jump by using the explainable AI and learning those black box, in fact, which by itself is really important and helpful. But also, again, that's kind of like a post-processing steps. That's a lot of work to do. To learn about that, because that was like one of the limitations that I said, they're not easy to interpret. And we need to do some post-processing to learn about the model, that what they have learned and why the results are really good. Because in the physical-based model that we are using for forecasting, we know that what's going on within our model, in fact. For the deep learning and AI, we need to know. We need to do some post-processing, in fact. So we have done that, we'll learn about it, for example, but one of the things is, which I will back to this point, and I will explain it more in detail, is one of the limitations. So we know that, at least for some of the applications, the relative orientation of those physical patterns from the meteorological, environmental, or atmospheric variables that we have, and their location within each map are really important. For example, for fog forecasting, the pattern within the sea surface temperature, the pattern of the wind, the pattern of the temperature in the coastal area, or all those dew points, or everything's like that, they're really those locations and their movement towards the coastal area, for example, to making a fog, they're really important. We need to learn that. But one of the problems related to the CNN's model that recently people are really so happy about it, which we were, and we did a good job to publish 2 papers and the results are really good, is that this person is Jeffrey Hinton, which is a godfather of AI, released this talk, which is what's wrong with CNNs. In fact, CNNs has been developed for natural images and natural kind of like machine computer vision tasks for a natural imagery with the RGB bands. In fact, CNN does not encode the position and orientation of the objects, and they suffer the lack of location sensitivity, which is really important for meteorological, atmospheric, and environmental model, but not for example, natural images, object detection, or etc. For example, what I'm saying is this. If you look at these 2 pictures for the CNN, to say this is a face, to detect this object, these 2 pictures are exactly the same. Doesn't matter. Doesn't matter if the eyes is kind of like in the different location of the map, right? But the CNN, by using those kernels, like filters and receptive field and pooling, will learn that, okay, there is some eyes in this picture, there is some lip, nose, and head. Okay, so that's a face. That's it. Doesn't matter what they are, in fact. Doesn't matter what's their relative orientation of those patterns and features within each map, which for our case, for for environmental modeling, we need to take care of that. The paper come up, attention is all you need. We need to pay attention of only those information which are related to the forecasting, not more. We don't need anything else. That's it. This paper was published by Google Brain in 2017 for language processing, in fact. I'm kind of like not going into the details what's going on within architecture, but this architecture is doing totally different learning. It's trying to generate and initialize a 3 different vector, which is a query key and value, and force the model to learn the query based on the values. And probably recently you have heard about the ChatGPT or GPT-4, for example, those family, which kind of these days are kind of covering all the news, are from this family, this attention-based models, in fact. But yeah, so instead of like talking about the architecture, I will mention some points here, which is really important for us. First of all, some people develop the attention-based models for imagery instead of like only for language, for example. But what's important for us is that the attention-based model dynamically generate the sample-specific parameters instead of fixed filter used in the CNN. What that doesn't mean is, in the CNN, since it has been designed for RGB imagery, and the model will look at each band of the image with the same eye, in fact, let's say like that, because it's using the fixed filter, fixed same filter for each band, right? So, but for the environmental modeling, it's not fair, because it's not fair to look at the SSC and temperature at the same filter, because they're providing a totally different patterns. They're providing a totally different gradient, right? So we need to have some filters which learn based on the sample itself. And attentions, by using some dynamic filters, which will be learned through the training of the model, will learn those patterns for each of the samples, which is really good and kind of like scientifically related to our projects. And also the attention-based models, learning the interaction between all the entities of a sequence at the same times. For example, in this sentence, which is a translation of the ChatGPT, the attention will learn the interaction of each of these words in this sentence with others. How much those words in the sentence has been important related to other words in the sentence to predict the next word. That's how the attention in language processing is trying to do. For our case, this is important because at the same time, when we have a lot of variables and we want to take advantage of those variables, to learn about the interaction between all those variables at the same time without any limitations. Because as I said in the 2D, for example, or in the conventional modeling, we were limited to the number of the variables. We had some expert person and say, okay, for fog, just, you know, we know that physically that SST, wind, dew point, you know, like several others are really important. We don't need the rest. But we have shown that for environmental modeling, if we are using the AI, it's really better to, you know, feed as much as variable that we have and let the model make a decision which variable is important and related to the forecasting case or, you know, the application in general. Also, the attention-based model are invariant to permutation and changes in the number of the input. What that means is we shouldn't be worried about the order of the variable that we are using. You know, like pick up as much as variable you want and just put them in the model, and then the model will learn that interaction regardless of the order of the variable that you are picking, which that's kind of like solving the limitation of the CNN-based model that we talked about. And also one of the concerns related to the attention was that, okay, the attention trying to vectorize all the input variables, which that means we kind of like doing the same things with the one-dimensional and put it on a CSV file and tabular data set by messing up with the spatial pattern, etc. But it has been shown that, which I will show you some results, the attention modules and transformers, by using the multi-head, will learn about the local and global features within each map. Which there are some new generation of the CNNs, which they call it deformable convolutional, which that's kind of like similar to this, which we are fine to use the attention to learn about the spatial pattern as well, which that's good. So here I started to work on tools which we called it SparkMet. The sparks come from the Transformers in the movie, which is a action movie, and METIS goes for the meteorological and environmental tool. In fact, these tools trying to have any kind of like data structure input data set, 1D, 2D, 3D, 4D. So it depends on the user and depend on the availability of the data set and amount of the data set and whatever it is. And for different tasks, it is totally based on transformers. It's user-friendly. I try to do that and kind of like decrease the amount of interaction between user and tool to take advantage of this tool and return some report. So it's, for example, asking, okay, you want to forecast the precipitation. That's fine. Okay, where is the data set? That's the data set is there. So you just need to send out a directory. And then saying, okay, I want to use the data set from 2009 to 2020, for example, and I will go for a 24 hours lead time prediction, and I will go for a one-dimensional data structure like that. So, and the tool gonna take care of all those, like information that you gave to the model, and will generate the data set based on the directory that you introduced and prepare the data set for the model, splitting and training, and then, like returning some report for you, which is the accuracy assessment, etc. And you will introduce that how many variables you want, which variable you want to pick up, and etc. So that's something mainly based on the NetCDF files that we mostly dealing with for meteorological, atmospheric, or environmental modeling. This tools is doing okay these days, and I'm kind of like finishing it, and I add some XAI tools as well, and I will show you how it kind of work at some point. But let's back to the transformers and attention. So let's imagine we have a map with 32 by 32 different pixels, which is the grid of the map that we have for meteorological and different maps that we have for applications. And let's say we picked up 5 different variables for simplicity, but we can have any variable, any amount of variable that we want. In the kind of original way for using the transformers or attention, the people try to split the map into some small patches, and then learning from those patches and learning the interpolation between those patches to each other, because again, the attention has been developed for RGB imagery, not for meteorological or environmental, with different amount of variables, and those variables providing a totally different patterns, not like RGB. So I try to go and fit the model, the whole map as a totally one entity, one token, let's say like that. What that doesn't mean is it's trying to learn, because I want to have each variable as a one separate entity for the model, to learn about the interaction between all of them at the same times, and also within each of them spatial. So we are learning the spatial, temporal, and even the correlation between the variables at the same times, if we fit that in this way to the model. So based on this strategy that I try to implement, this is the exact same data set that I use for fog forecasting. Okay. And this is the attention scores for SST map. So the model really did well. So I didn't put the result because it's kind of like the same as the 3D CNN FogNet that I showed you the result here. But what I'm trying to say is, because we talked about a couple of things. We wanted to have a model which is really interpretable and easy to implement, like a conventional machine learning, like linear regression, for example. And also we wanted to learn about all those 4 dimensions that we talked about it. So here, the attention is trying to do exact all those point that we mentioned. Here is one of the result of the interpretation of the attentions, because the attention by itself will return the most important area within each map related to the fog forecasting, for example. This is a coastal area that I showed you, and this is a SST map. And based on the physical concept, at least in the second paper, we have discussed that the most important area related to the FogNet should be this area in the top left corner, because the airport is there, and we want to predict fog there. And attention by itself, without any post-processing, will return that, if the model has been trained well, will return that, okay, in the top layers, the model has been learned that the SST map has the most, because that's kind of like the highest score, the yellowish area in the lower, raw, in fact, the layer 4, you can see those area has been mentioned as the most important area within that map, right? But that's exactly what we wanted to see. We wanted to learn, and the model has learned that through the training. And the good point is, since we have several different heads, like an ensemble model, and each of them has learned totally different view of the data set, which that's really good. And the final result is based on the average of all those, heads that we have, which is, look at it like a ensemble model with different, like a TREF, which has, I believe, 8 different models, if I don't mistake, or a STREP, which is 6. So that's one of the good points related to attention models, which just pay attention to the most important and related area within each map toward forecasting. One other things that I mentioned that was kind of like important to us again, which is that learning the intercorrelation between all the input variables at the same times without any limitations, because that's why we want it. In 1D or 2D or 3D dimension models that currently we have, we are limited to learn about those dimensions, like higher dimensions. But in this sense, you can see I have 380 different variables, and you can see the intercorrelation between all those 384 different variables at the top layers. So this is something like a linear regression, for example, that we are using. It's totally easy to interpret that what's going on, those coefficients, for example, that we have, how much they are related to each other, etc. And in this model, so we have this ability to go through all this interpretation to see so which variables had, through the training, the most correlation with others, which variables are really important, which are not, for example, which that's really helpful for modeling and learning about the models and learning about the physical concept behind of this forecasting by using the AI, which that was kind of like challenge for all these years after, using AI-based model for forecasting. One more thing that we can do based on the attention is, so through the training, you want to know especially the correlation between one specific location with others. Like, okay, in each head, where is exactly the most correlated and most attentioned area within each map related to that specific pixels, for example? This is SST map, And in each layer, you can see, for example, specifically for this pixel, which is the airport, we can see the most correlated at the beginning and at the end. At the end is most, like, it's more broad. It goes over different location in the map, and we can see which area within a map are really important within SST map related to a specific epochnet, airport, which is the visibility comes from that specific location. So in this sense, we are able to learn about first those relative correlation between the different pattern within a map. We are able to learn about the intercorrelation between all the different variables in totally four-dimensional domain, and also you know, having a really straightforward and interpretable model, which is much more really interesting, at least to me, which I love it compared to the CNN. So as I said, they're really straightforward, easy to implement, not limited to the dimensionality of the input data set. They're learning the intercorrelation, and also they are really interpretable. And I think is kind of like all my presentation, probably fast, but thank you so much for your time, attention, and I'm open for any question.
Thank you very much, Hamid. I'm going to ask if there are any questions from the floor. I can't quite see people here first. Can you stop sharing for a moment?
Of course.
Okay. Any questions from the audience?
Hi, I have a question. I'm Edmund.
Of course.
Hear me?
Yes.
Yeah, it's nice talk. Yeah, and you kind of describe sort of you can learn from the algorithm where the
I'm unable to close apps here. Sorry.
Sorry, it's my iPad.
Oh, okay. Yeah. You can learn where the SSTs are important, but presumably that would be related to things like wind speed and wind direction and things like that. So can we actually learn all those interconnections? As you said, you can learn the correlations between the different variables.
No, that's really a good question. Exactly, that's the next step. I really want to go through the visualization and getting it out. And that's exactly, I want to learn. Okay, so for example, for fog forecasting, we will pick up the 10 best variables. Let's say based on this interpolation, the model will tell us, okay, these 10 top are most related and most important and most attention variable that we picked up. And then from there, I really love to visualize, but yes, we have those information to visualize the interpolation between the pattern of the SST and wind, the SST and viewpoint at the same location, for example, or different locations. That's a really good point to go and visualize it and, you know, learn from it. I really like that point. Yes, we are able to visualize it. We have that information.
So hi, Kamazima, I have a question also.
Sure, Sultan, go ahead.
Hi. Thank you so much, Hamid. It's a very interesting talk. I have a very simple question. So like, I'm just focusing on one thing. You said that, okay, you found that the data at the airport is best correlated with these other points you located, right? And so you want to pay attention to that. But in a different selection of data sets, like for a different month, these points will be different, right? I mean, which are best correlated with the airport will be different. So it is a continuously changing system.
That's a good point. So based on the training data set that we are trying to use to help the model to train about, learn about the patterns, in fact, those correlations, yes, so the time should be changed, but at the end of the model, we are able to, at least personally, I will go for the average of those correlations and return the top 10. That's the way that I'm using. Might be, like not scientifically correct, but that's the only way that I came to my mind to return the 10 top based on the average of intercorrelations throughout the time. But really, yes, throughout the time, the correlation should change and would change.
So, but that is the same thing we get in conventional analysis, like in EOF methods, like that. So there are these relationships we can find between different locations and in 4-dimensional data, but then they change with time. So there's no like permanent model you can have. It has to be retrained again and again, right?
That's true, but at least in terms of changing those correlation, I believe, since, for example, when we training the model with totally different training data set, you know what I'm saying? Like when we cross the data set through the training and validation and we change it throughout the time, for generalizability and generalizing the model in terms of changing throughout the time, I can say the performance of the model is really stable based on the deep learning models. But the point that you mentioned is really interesting, because if we go back, if you go back through the time and, in the details, checking out the intercorrelation for one specific time, that might change model by model. But in general, the model will learn the pattern that it needs to learn. And the result, for example, when I'm training based on 10 iteration, for example, the standard deviation is really low. I mean, the model training is really stable in terms of the performance, but yeah, the correlation too.
Well, thank you so much. I really enjoyed the seminar. Thank you.
Thanks for your time and great point.
We have a question from Brian.
Yes, hi. No, I enjoyed your seminar as well. Although maybe I got distracted at times or something and I missed a couple things. I just wanted clarification. What do you mean by prediction? What kind of lead time? And I know I'm kind of familiar with the href, for example, which is, a model or ensemble. I think that's the ensemble system.
Yes, it is.
So I'm trying to draw more connection between what you're doing and what NOAA does, within these models. So maybe I'll start with that. So what's your lead time, or are you predicting nowcasting or what?
No, it's really lead time for next 24 hours. Okay. We tried to develop that model for 6, 12, and 24, which in the paper we have all the results, but here I just put the result for 24 hours. And we categorized or binarized the fog visibility, in fact, in terms of the fog and not fog. So we had like a binary classification, but the lead time is yes for the future. So it's not nowcasting.
So the data that goes into your model for the future is what exactly?
So for example, for next 24 hours, I have the initial NAM prediction. I have 6, 12, and 24 hours lead time prediction for now, and I will predict the next 24 hours.
Okay, so you're using another model, the NAM, at 12-kilometer grid spacing, or maybe 3 or something, to do that. Okay, yeah, well, maybe I'll contact you later to learn more, but I guess I'm trying to, one thing, just as maybe a comment or a question. We know that these weather prediction models have struggle in fog situations because of the boundary layer and mixing, and what you're doing is sort of like a bias correction, where you're dealing with the fact that the href or NAM doesn't have that, or is mixing too much, and you're trying to identify situations where you can fix that. I just want, one thing I'm interested in, and maybe get your thoughts on, there's such fundamental problems in some sense over the water with some of the mixing. There is an opportunity to do what you're doing and actually fix the model, like the mixing lengths, the parameterization, to actually probably make these models a little bit more competitive and in general. And so I'm just wondering, have you or done anything. I know NOAA is very interested in that, using machine learning to actually fix the primitive equation models that have these sorts of parameterization.
So to be honest, no experience on that, but what I have read about these concepts, what I see is the people have shown that directly using the machine learnings for the raw data set has been more challenging compared to using the NAM output, which some of the problem physically has been solved, and we will, compensate those limitations from the physical models and make it better. If that's probably the answer of your question, but I also have seen some, for example, implementation, they try to involve the physical information to the model by using some custom loss function and helping the model to learn about the physical behind of this problem, which can be fog or anything like that.
Yeah, no, for me, fog forecasting really boils down to 5 or 10 variables. If you have 90 some variables, to be frankly honest, it's like a spider web, a black box. So anyhow, I'll let someone else comment. Thank you. Of
course, thanks for your question.
I will comment on Brian's last comment, but I want to see if there's another question from the audience.
Yes, Kamazima, I do have some questions. This is
Ping, go ahead.
Good, thank you. It's a very interesting talk. Thank you again, enjoyed it. I got a couple of questions. First one is a more technical question. How many GPUs or CPUs, particularly GPUs, did you use to run your model for that paper?
So that's a good question. For this one, actually, I have 4 GPUs.
4 GPUs. So
10 AT.
Yeah.
Okay. And the training time was like, let's say, almost 10 minutes for each epoch. So maybe, less than a couple of hours. So
nice.
It wasn't terrible.
Yeah. You use like 50 epochs?
More than that.
More than that.
But I had like a stop learning. So kind of like avoiding overfitting at some point. So
yeah. So the second one, you mentioned that we need to do some post-processing when we get the model results. Can you be a little more specific? What type of post-processing we need to do for that?
Yes, for sure. So based on the CNNs, since it's totally black box, if we want to learn about what this model has learned, because we don't have any sense of the patterns that which has been learned, for example, in this sense, we need to do some post-processing, which we have done it based on the XAI, which actually in the paper, we have a lot of details, and new paper is coming up, which is more detailed paper related to explainable AI on top of the CNNs. CNNs are totally black box. We need to go inside the box and see what the model has learned, right? By using the permutation features, by using for example, all those, interpretation techniques that we have already for machine learning. And also the new techniques has been developed specifically for image, which they call it SHAP, which is based on the Shapley game theory, which trying to learn about the kind of contribution of each of the variables to the model. You know what I'm saying? Yep. So you need to do some post-processing to learn, okay, what the model has learned. But the good point about the attention is that since it's trying to pay attention of those area and variables, it will return those information to you. So that means we have all those information at the end of the training. We don't need to do some post-processing. We have the most important area within each path. We have the most important variable. We have, the intercorrelation between the variable in a spatial domain or temporal domain, that's really good. And it kind of like, decreasing all those post-processing at the end and even more, reliable at least.
Nice. My last one is about this site, attention transformer, and the CNN site sounds pretty new compared to the CNN. So can you give us a little bit more background or connections between these two? Is this site under the framework of CNN or a completely new deep learning model?
Yeah, this is totally a new generation, actually.
Okay.
because this specific generation, which they call it transformers, first of all, doing a totally different way of learning. I mean,
Okay.
it's not learning a filters like a
Mhm.
kernels, for example.
Okay.
There is no kernel here. You're just
Okay.
vectorizing the input, trying to generate a tree vector based on the input variable that you have,
Mhm.
and query key and value, and forcing the model to learn a query based on the value
Mhm.
by using some softmax. So it totally has been developed for language, actually, language translation, in fact, but the people trying to, invest it on for different tasks, which worked really well.
Okay.
But it doesn't have those kind of the way that CNN is doing for learning. That's why, it's more exciting, actually.
Yeah, good thing for CNN is that it substantially reduced the variables dimensions, such as we have very high resolution images, we have very high resolution atmospheric model outputs, etc. So CNN is good in reducing those dimensions into a very small number of neural nodes later. But in the side occasion, is there any such mechanism to reduce dimensions of data?
So that's really one of I didn't mention it here because we didn't need to talk about it, but transformers doesn't care about the structure of the entity together.
Okay.
What that does it mean is that, okay, for example, for FogNet, I have a NAM with a 12 kilometers resolution, spatial resolution, and I had SSD more data set with a 1 meter resolution, right? I had to do some manipulating, processing to making a consistent spatial resolution for these two type of data sets, so the architecture.
Mhm.
But the good point about the transformers is that doesn't matter, because even it will read the data from totally different data structure. For example, you can have a categorical information at one entity, and you can have a map, for example. You want to generalize the fog cases for the United States, and you have one coastal area in the east, one west, one, you can have a categorical information like, okay, here is the coast, New York, here is the Texas, and here, and the transformers will change that categorical information to the pattern for itself, and will learn about it to make it more generalized. For example, that's kind of like an example, but yes, it has this ability to take care of those type of problems.
Good to know. I definitely will contact you later for more information. Thank you again.
Of course, thanks to you.
Thanks, Ping. Anybody else with a question? Okay, I don't see. Before I ask my question, maybe just let me make a comment on what Brian said, because he asked about the 93 variables. I just wanted to say the 93 variables actually don't necessarily have to come from 93 different variables. It could be just in terms of time lag and stuff like that.
Different altitude.
Different altitude, yeah. So essentially, I'm just telling Brian, he shouldn't be scared of the 93. It's not that many.
That's
Well, I agree, but it's still a little magical. What
Exactly.
it boils down to is just the lowest couple levels, and whether you're saturated or not.
Yeah. Actually, the paper, the 2022 and the 2021 papers, they both do a very good job in describing what they've done, and what's the physics behind in choosing those variables. So if you take time to look at the papers, it will be more understandable. But I had one question, and Ping asked one of mine about the high dimensionality. So I'm gonna go for one of the last comments you made, where you showed a lot of images coming out, and you were trying to show where the transformer tells you to pay more attention, like you started with the bottom row. Yes. But I was thinking, if you take the more and then do the average, yes, that one. If I take the more and do the average, am I watering down what I should really be paying attention?
One more time, I didn't get it.
If I take the average, let's say I take the first head.
Okay.
If I take the average, am I smearing out my information and
So the way that, first of all, I'm talking about the layers and then the heads. So we have row and columns, right? The layers, we will use the layer 4, which is the end layer for the prediction, because the layer 4 has been learned from the layer 3 and layer 3 from 2 and layer 2 from the layer 1. That's the first thing. Second, compared to the heads, it's not a simple averaging to smoothing the information. Again, it's based on the scores. For example, the first head has a more scores compared to the head number 8, for example. It's more like a weighted average.
Okay.
For making the final decision. And also those scores epoch by epoch, so the training will be updated. You know what I'm saying? It's like will be optimized. So
okay. I wanna thank Hamid again. I can't see if there's any other question, but thank you very much, Hamid. That was really exciting, and I'll follow up with you on some of the other things.
of course, thank you so much for having me and all you for your time.